Hi, my name is Alex, and I will present our paper, Characterizing, Exploiting, and Detecting DMA code injection attacks in the presence of an IMU. This work is the result of a collaboration between the Technion, VMware Research, and Tel Aviv University. So first, we start with a DMA. DMA, or Direct Memory Access, is a common hardware feature that allows an attached device to access the main memory without involving CPU. That's devices like GPUs, SSDs, network interface cards, USBs, and other dongles. These devices have their own memory, their own CPUs, and can therefore run their own code. DMA also allows a malicious device to read or modify memory that was not intended for its use. This is called a DMA attack. It's a side channel attack where a malicious DMA-capable device compromises the system. One notorious example is this thin FireWire unit, uh, which is basically a Lenovo ThinkPad with a FireWire adapter. And it can be used to take over the target machine. Just approach the target machine, plug in the attached dongle, and gain control. Fairly simple. To prevent such arbitrary access to the memory, modern systems have IMU hardware. The IMU works for devices just like the IMU works for processes. It provides virtual memory support for the attached device, meaning that the device can access only pages that are listed in the IO page table. This page table is controlled by the operating system. Within IMU, the device can access the main memory only via IO virtual addresses, IOVAs. And this prevents the device from accessing any memory pages that were not explicitly mapped within IOV by the OS. And this way, the IMU is supposed to prevent DMA attacks. So first, let's see how IMU is used via DMA API in the Linux kernel. And then I will show you why IMU is actually insufficient to provide security. The example I'm going to show is a path of a send packet. So first, the device driver maps, DMA maps the virtual address of the buffer it wants to send. The operation creates an IO virtual address, a new number. It updates the page table, that's the blue box on the side. And now the red virtual address and the yellow IOVA point to the same physical address. Next, the device can send. It reads the packet. Once the packet is read, the IOTLB is populated. The IOTLB is just like the TLB with IMU. It is used for fast lookups. Then after the completion of the send, what happens is that the DMA unmap call is invoked by the driver. The IOVA is purged from the page table and then from the IOTLB. Without flushing the IOTLB, the device can still access the physical page. And then the IOTLB, the IOVA itself is free. Now, after the DMA unmap, the NIC should not be able to access the physical page. The security problem with this approach is that the IMU has a 4K granularity, while IO has much smaller buffers, can have much smaller buffers, and like R packets, DHCP, ICMP, or any other small packet that you may want to send. In this case, the NIC will need to access just one small portion of the page, but will have access to the whole page. And unsurprisingly, recently, several research groups were able to take advantage of subpage vulnerabilities. One example is the Thunderclap project that appeared in NDSS in 2019, and the authors scanned and found multiple DMA vulnerabilities in different operating systems. One of the methods they used were to masquerade their FPGA as an old Intel NIC. Cooper, on the other hand, in his master's thesis, was able to take advantage of a DMA vulnerability in the FireWire device driver and was able to create and demonstrate a code injection attack on the target machine. The problem with both of these works is they have an ad hoc nature. They found something and they shown how to exploit it. The problem is that now you don't really, the question remains, how do you go about finding DMA vulnerabilities? When you have a DMA vulnerability, is it something that is useful? Can you exploit it in any dangerous way? And the main question was how many vulnerabilities left unfound, left in the dark, how cheap that we are on. And I'm here to provide at least partial answers to these questions. So in our work, we first make order and chaos. We create categorization of subpage vulnerabilities. They're not all the same. And we describe what are the three attributes needed for a successful code injection attack. We provide tools for detecting DMA vulnerabilities. And we, with our newfound knowledge, we create a new DMA attack. We name a compound attack. So we'll start with characterizing subpage vulnerabilities, the classification, and the attributes. So there are four types. We introduce four types of subpage vulnerability. Type A is when a device reads a buffer, an IO buffer, which is also populated with the device driver's metadata. And it's a security bug by the driver. But more often is the case when you access an IO buffer and there's an OS metadata right in front of it. The example being a Windows and Mac OS both have this feature when the IO buffer metadata and the data itself reside on the same contiguous physical memory. And in this case, the device driver offer has practically no way of avoiding this vulnerability. A third type, type C vulnerability, is when two IO buffers map the same physical page. And the problem with this kind of vulnerability is when one of the IO buffers is unmapped. And this page is still accessible to the device via the second IOV, which renders the unmap operation from a security standpoint effectively useless. The third, the last vulnerability, the subpage vulnerability is incidental. Namely, these are cases when the malloc operation gives 64 bytes for IO and then 64 bytes for any other operation. And this IO buffer, when mapped, also exposes all other buffers of its size on the same page. This one is non-deterministic and is harder to find. So let's look at an example of how subpage vulnerabilities can cause a problem. So we take an example from the NVMe fiber channel device driver. One example is a Broadcom fiber channel device. And when a request is initiated, when the host wants to read something from a storage device behind the NIC, it will create a command. It is 96 byte long, and it allows the device to read from the page. Obviously, it's the API. And then it's practically the next line of code. It maps the response. It's 32 bytes long, and it allows the device to write. And it leads us to the following. We look at the command and response, and we find that they reside right next to each other on the same physical page. And they also expose the rest of the metadata, which is not intended for the driver's use, for device's use. One of these fields is data structure, is FCP request, and it contains a callback function that, if modified, will allow the modifier, the attacking device, to execute any code in the kernel. So that's a problem. And it leads us exactly to the free attributes needed for successful attack. For successful attack, we need the CPU address of our malicious code, not the IO virtual address, the kernel virtual address. And we need the callback. And we need an opportunity, namely that once we modified the callback function, it should be the only thing that should happen. It should be called rather than rewritten or initialized by the CPU. Right? And this is exactly what happens in this fiber channel scenario. So we map these two fields. We find the callback pointer, and we find this request pointer. And after looking at the code, you discover that the request pointer is actually a request structure, actually holds this op structure inside of it. So it's basically pointer to the same page that we are on. And so if the attacker finds enough space on this page without causing any havoc, unnecessary havoc, to write this malicious code, we have the three ingredients. We have the virtual address of our malicious buffer. We have the callback pointer, which we can modify with this malicious buffer. And in this case, this buffer will not be modified and will be called by the CPU, creating whatever havoc that the attacker needs. So next, let's talk about detecting DMA vulnerabilities. We have static analysis that can allow us to find vulnerabilities in the code. A dynamic analysis will allow us to find vulnerabilities at runtime. And obviously, we can find, we show the analysis of kernel 5.0 and what kind of vulnerabilities we found there with static analysis. So the first one is static subpage analysis, or SPADE. SPADE, it's for subpage analysis for DMA exposure, and it operates recursively, starting from calls to the DMA map function, which we've seen in the first and in the two examples I've shown. So from this initial DMA map call that is called from F fiber channel DMA map single, we see that pointer is mapped. And we see that pointer is a void pointer, which doesn't help us much, but we circle back recursively. So we look for FC DMA map single calls, and we find one at NVMe FC init request. And we see that the op struct is mapped. We go back and we see that the name of data structure. And using tools like PA-hole, we find that there are embedded callbacks in this data structure. And here's our vulnerability. For runtime analysis, we started from a Linux kernel tool. It's called Kazan, a kernel address sanitizer. Originally, it is used for dynamic memory error. It's a dynamic memory error detector. It's designed to detect out of bands and used after free bugs. It uses shadow memory to record whether a memory byte is safe to access. It also uses compile time instrumentation to insert checks of shadow memory on each memory access. We modify this tool and call it DMA Kazan. And now we also record DMA map operations, and we're able to find bugs like this: allocation after map, where a buffer was allocated from a map page; map after alloc, where a buffer was allocated and then later mapped due to another buffer that was mapped; access after map, when a mapped page is accessed by the CPU; and multiple mappings, namely type C vulnerability. We run some IO with operations like kernel compilation, and we could find a lot of examples where unnecessary access was given, like alloc SKB usually provides only read or write, and we found cases where it was both read and write, and actually can make a security problem worse. We found do execv and load elf behavior functions, which have nothing to do with IO, accessible for modification by the device, and other problems. Now to the results of the static analysis. We see that out of about 1,000 calls, API calls, we see that about 15% of device driver actually expose callback pointers in their operation. It's a type A vulnerability. But we find that about 45% map SKB shared info. SKB shared info is one of those cases where an IO buffer and its metadata coincide on the same page. And SKB shared info is an example for Linux. Private data map is one other example of type B vulnerability. Build SKB actually creates the SKB shared info inside a map buffer, so it's essentially the same thing. Those are type B vulnerabilities. We look for cases where the stack is mapped. We find several cases. And we look for explicit type C vulnerabilities, where unmapping in IOVA is actually useless for security standpoint. And what this table tells us that about 76% of device drivers are exposed even without random exposure. And about 62% are exposed due to design choices, by the kernel design choices, rather than device driver bugs. So the ship is leaky, to the question. And using all this information, we can now start building new, more complex attacks. The attacks I've shown you and that we've seen in the previous work are what we deem single step, where the three attributes are present on the same page. The virtual address of the buffer, of the malicious buffer, the opportunity is trivially given, and the and the callback pointer is present on the same page. In compound attacks, we take the example of SKB shared info. In Linux, where the IO buffer is appended with the metadata is added at the end of an IO buffer. Sorry for that. So the SKB shared info has a lot of useful information, like pages for scatter-gather operations. It also holds a destructor arrow, which is essentially a callback pointer, or functions as one. But there's no opportunity, because usually what happens, you first unmap the IO buffer, and then you initialize the SKB shared info. The second thing is you, as a device, don't have a CPU address. All you have the IOVA addresses, which are not useful for rewriting the CPU callback pointers. And I will not go into detail in this talk because I don't have the time, but you can read the paper and ask questions if you like on how to create a compound attack, where essentially it seems that you don't have the attributes for an attack, but you can get them with compound operations. Thank you. This is the GitHub for our tools for static analysis and the dynamic analysis. Thank you for your time.